Okay, can you hear me?
Yeah, we can hear you.
Perfect.
Okay, then for our last talk in this session, it will be given by Hendrik Molter, and it will speak about counting temporal paths. Please, Hendrik, the floor is yours.
Thank you. Yeah, so I'm going to talk a little bit about counting temporal path, and this is joint work with Jessica and Kitty from Glasgow University. And just to start off, I want to also briefly give the model that we use, even though it's pretty much the same as before, but just so you know the notation that I'm going to use. So temporal graph, we consider an edge-labeled graph or a sequence of graphs. And I'm also going to call the graph without the labels the underlying graph. In contrast to the previous talk, we go back to the model where we just have a single label, which indicates at which time this edge is active. And a temporal path, because we're counting, it's kind of important to really define properly what it means. So I'm going to assume that the sequence of time edges, so edges with the labels, is a temporal path. And then we call them strict if they're increasing, and non-strict if they are non-decreasing. So this is a definition by example. This is not a temporal path. This would be a non-strict temporal path, and it will be a strict temporal path. And again, just I want to point this out a little bit because we are counting, we want to know when we consider two temporal paths to be different. So even though, let's say I use the same sequence of vertices, but I exchange this last edge here, say, for a different one that uses label 5, this will be a different temporal path. Okay. And now, why would we be interested in counting temporal path? And the main motivation I want to give you is temporal betweenness computation. So betweenness is a centrality measure that kind of tries to quantify how important a certain vertex is in a network under the assumption that information travels along optimal path. So in the transportation networks, we may assume that most people try to arrive at their destinations as quickly as possible, and then you might want to ask a question like, how important is the Berlin main station for the German public transport network? Or more generally, if you have a vertex in a graph, then betweenness roughly quantifies how likely it is that a random shortest or optimal path in general passes through that vertex. And in the temporal setting, we have different choices for what it means that a path is optimal. And that was already touched on a little bit in previous talks. So if you consider this small temporal graph and ask yourself, how can I get from S to Z? There are these three obvious choices. And the first one is the one that uses the minimum amount of time edges. So we call those shortest temporal path. The middle one arrives as early as possible at time 4. So we call that the foremost temporal path. But then the lowest one has the shortest transition time. So we kind of disregard how long we wait in the very first vertex, because we assume that we could just go to the train station later. And then the difference between the first label and the last label, so the time that we start and the time that we arrive, is minimum in fastest temporal path. And then I want to show you also quickly the definition of temporal betweenness centrality, but the important point here is that we have to be able to compute these values here, which denote the number of optimals. So the star here denotes the optimality criteria that we are interested in of temporal path from a certain vertex to a certain other vertex. And you can actually show that computing this betweenness value is as hard as computing these values. So there's no kind of way to get around that in some sense. So yeah, we can observe that computing temporal betweenness is essentially equivalent to counting optimal temporal path. And for many interesting optimality concepts such as the foremost or the fastest, which I talked about earlier, it's already known that computing this value is sharp p hard, and sharp p hard is or number p hard you can think of as the analog of NP hard from counting problems. So we don't believe that we can compute these numbers in polynomial time. So this leads us naturally to the question, how can we count temporal path efficiently? And we look at this very simple problem. So we're just given a temporal graph and two vertices S and Z, and we are interested in counting the number of temporal SZ paths. And if you think about it a little bit, if we can solve this problem, we can also count the number of foremost temporal paths just by removing all late time steps, because computing one foremost temporal path can be done in polynomial time. That was mentioned in earlier talks. So we can just do that, remove all late time steps from our input, and just count all the remaining paths, and those are all going to be foremost paths. So if we can solve this, then with polynomial overhead, we can also count foremost temporal path, and by a very similar argument, we can also count the fastest temporal path by just moving essentially the duration window across the temporal path graph and removing early and late time steps that we're not interested in. And then what's also important, that for the betweenness, I went over it a little bit quickly, but to compute betweenness, we also have to compute temporal path that visit a certain vertex, and that we can do by removing that vertex from the graph and counting the remaining temporal path, and then taking the difference essentially. So I told you that essentially to convince you that if we can solve this problem only with polynomial overhead, we can also compute the temporal betweenness for foremost and for fastest path. And for this talk, I will focus on non-strict temporal path, because then I have the nice property that counting temporal path generalizes just counting path in the static graph. And that already gives us our first observation, that counting temporal path is sharp p hard even if I only have one time step, because counting path is one of the classical sharp p hard problems introduced in the 80s. And so whenever we encounter hard problems, we can do essentially the same as in classical decision problems. We can look at parameterized algorithms and we can look at approximation. We did both here, but for this talk, I want to focus on parameterized algorithms or parameterized complexity results for this temporal path counting problem. Okay, but as a warm-up, I want to show you how to count temporal path if the underlying graph is a forest. And we can make a simple observation that if the underlying graph is a forest, then all temporal SZ paths will follow the same sequence of vertices. So we can kind of reduce our problem to the problem of where we are giving a sequence of vertices and we want to know how many temporal paths there are that follow the sequence of vertices. And that we can do by dynamic programming. So we just use a table with two entries, V and T, and we want to know, so this table entry is supposed to be the number of SV paths, so paths starting at our start vertex and arriving at some intermediate vertex V at time T or earlier. And then, yeah, it's not very complicated to verify that this makes sense. So the initialization from V to V at any time we have one path. So we consider the trivial path that only consists of one vertex as a path. And then if I want to know how I can get to VI at time T or earlier, I look at all the edges that lead me from VI minus 1 to VI at some time T prime, which is at most T. And I just add up all these paths that lead me to VI minus 1. And I know that all these are pairwise different because at the very least, this last edge here is going to be different. And so we know that we can solve this problem in polynomial time, or we can count temporal path in polynomial time if the underlying graph is a forest. And that leads kind of naturally to the question, can we generalize this idea somehow? So can we generalize this forest algorithm? How can we do that? And yeah, so next I want to show you our Manhattan's results that we have to kind of set a baseline what we can expect. And what we could show as one of the main, I would say, technical results of our paper is that temporal path is hard for complexity class called parity W1 when you parameterize the problem by the feedback vertex number of the underlying graph. So parity W1 is kind of the problems which are equivalent under parameterized reductions to deciding whether the number of cliques of size k is even or odd in a given graph. So you want to, or here in our case, we want even computing the, if there's an even or an odd number of temporal path is hard for this complexity class. So also counting the temporal path is hard, because if we can count, we can also determine the parity. And of course, this uses then the assumption that parity W1 is not equal to FPT, but even that I would say is relatively widely assumed to be true. And I want to give you the main ideas how we get these results, and also touch a little bit about on the problem that we could only show parity W1 and not sharp W1 hardness. And maybe some of you have an idea how to fix that. So the main idea is that we reduce from a problem called independent set on two-track interval graphs, which is known to be W1 hard by the solution size, or by the size of the independent set. That was shown by Jiang in 2010. And a two-track interval graph is a graph where every vertex is represented by two intervals that kind of run on these two different tracks, an interval AV and BV, and two vertices are connected by an edge if either the A intervals intersect or not either or. They can, if the A interval intersects or the B interval intersects, or both intersect. So on at least one of the tracks, the A track or the B track, the intervals have to intersect, and then there's going to be an edge between the two vertices. And when we investigate this reduction here, you can see that what they actually show, or what they also show, is that the multicolored version of the problem is also parity W1 hard. So we can reduce from the multicolored version of that problem. Multicolored here means that the vertices are colored, and we want our independent set to consist of one vertex of exactly one, each color. And the very rough idea is that we have these two tracks, and we want to model one of these tracks with the vertices and one of these tracks with our time steps. And I want to give you a very rough idea how that can be done. So we just create a temporal graph where we have the vertices of our multicolored independent set instance like this. And then we introduce some auxiliary vertices, and here these W vertices, these are exactly K, and K is the number of colors. Then we just add a start vertex and this intermediate vertex Z prime and our destination vertex Z. And now if there's a interval, or for this example, I want to consider two vertices that have each two intervals. And so for this vertex A, which has color 1, we start at this color 1 vertex, and then we go via some intermediate vertex to the vertex corresponding to the starting point of the first interval, and it goes until the vertex corresponding to the endpoint of the first interval V4. So we model the first interval with the vertices here, and the second interval 2 to 5 we model with our time. right? And then if we have the second one, the blue one, it would look like this. So it has color 3, so it goes from the vertex W3, and the first interval starts at 3, so it goes here until the vertex V3, and then it goes until V6. And the second interval is modeled here in this time difference that you need to get from W3 to the vertex V3. And now if you want to look at the direction, can I put these two vertices into my independent set? Then the answer is no, because actually on both tracks, these vertices intersect. And if you think about temporal paths that are kind of composed out of these segments, then if I want to take this here, this red path segment, I'm already at time 5. So if I'm kind of following the rules that I'm trying to impose on this reduction, I will arrive at time 5 at whichever next color vertex I want to take. And then if the second interval intersects, then I'm not going to be able to take this path here, right? Because the starting time of this first edge is going to be earlier than the time of the second edge here. So kind of for the second intervals, if I follow these rules of following these path segments here, then I know if the second intervals intersect, then I cannot first take this red path segment and then follow it up with the blue path segment. But of course, what I can still do is cheat in that way. Like, for example, go from W3 down here, I arrive at time 4, take this here, this edge here, and then just go to some vertex WK like this. And now I selected the path segment that does not correspond to any of my original vertices of the graph. And this is something that, of course, is a problem if we want to do a reduction, right? And here we try to do some trick that allows us to circumvent that. But let me maybe finish the idea. So the idea is that we start at S, and then we go to a color vertex, then go through one of these path segments corresponding to a vertex, and then at some point to Z. And this path here should correspond to an independent set, not necessarily containing all the colors, but to an independent set in the original graph. And now, as I said, the problem are these paths here. And for those, we try to do the following. So in this picture, you have to think about the time kind of goes that way. So I didn't want to write labels here, but the blue labels are, I did actually write the labels. So the blue labels are at time 4, the red labels at time 5. So what, of course, I could do is go here and then go until the way here, then go that way and arrive here. And that would be a path segment that does not correspond to a vertex in the original graph. So what we did is we added other time labels to these edges, which kind of behave in that way. So they are kind of decreasing. And now whenever I start, I enter this path here, and I start going along this edge, and I deviate from what is intended to be the path corresponding to the blue vertex. Then I can either immediately jump to the red one, or I can first use this time label here, but then I cannot, because the next one is going to be earlier, I cannot do anything else but also jumping to the red one afterwards. And this means whenever I cheat, in that sense, the number of paths that do that is going to be even. And this is how we get that this doesn't matter in our correctness. We can disregard those in the sense that we know that they are going to be even, so they don't change the parity of the temporal path that follow the rules that we intend them to have. And this leads us to the lemma that the parity of temporal SZ path in this reduction equals the parity of colorful independent sets that don't necessarily use all the colors. And then we use some kind of Turing reduction where we remove some of the colors to compute the number of independent, or the number of paths that actually correspond to independent sets that, or the parity of the number of temporal SZ paths that actually correspond to multicolored independent set that use all colors. Okay, so that's all I wanted to tell you about this hardness reduction. I hope that gave you some idea there. I obviously left out a lot of technical details, but this gives us a pretty high baseline, because it means that for all parameters of the underlying graph which are smaller than the feedback vertex number, such as, for example, tree width, we cannot expect to get FPT algorithms. But what we could find on the positive side is that we can get FPT for the parameter feedback edge number, which is larger than the feedback vertex number. And we can get an FPT algorithm for the so-called time feedback vertex number, which is also larger than the feedback vertex number of the underlying graph. And further algorithmic results that we have is we can show the FPT with the tree width and the lifetime combined. This uses an MSO formulation. We heard about MSO in also one of the previous talks. And then the last algorithmic results we got is that it's FPT parameterized by the so-called vertex interval membership width, but I don't really want to go into detail what that exactly means. And as time permits, I want to talk a little bit about this result here for the remainder of my presentation. And to do that, of course, I first have to tell you what the time peak by vertex number, or the time peak by vertex set is. And the time peak by vertex set is, or this should say minimum time peak by vertex set is the minimum size set X of vertex appearances, so vertex time pairs, such that if they are removed from the graph, which means that I remove all incident edges from that vertex appearance that have the same label as the vertex appearance, then what I want that what remains is a forest. And you can already, if you think about it a little bit, you can see that this is larger than the underlying feedback vertex number, and it's smaller, or at most the underlying feedback vertex number times the number of time labels, or the age of the temporal graph. And if you try to visualize it, it kind of looks like this. So you have your time feedback vertex set as vertex appearances somewhere here, and what remains of the temporal graph is some forest structure. And what we can do now in our algorithm to count the number of temporal SZ paths, and here I also assume without loss of generality that S and Z are both, so S at time 1 and Z at the last time step are both contained in the time peak by vertex set. I can first go through all variants or all orders in which I want to traverse these vertex appearances in the time peak by vertex set, some of which might use connections which directly connect time peak by vertex appearances. And if they are not directly connected, then I somehow have to go through this forest. And this, to compute the possibilities of these connections here, I can use the polynomial time algorithms for forests that I showed you earlier. So I can use the first algorithm to compute all ways to close these gaps here. And then for all valid ways to glue together a temporal path here such that these don't intersect.
Sorry, just a quick note. You have 5 minutes.
Okay, I think I can manage that. All right, so just real quick. So for example, if you want to use this green segment here to connect S to this first one, then I cannot use this blue one here, because then I intersect here. So I can only use this one here, for example. And so I have to find out the ways I can connect these, and then I have to use the product. So if there are n temporal path connecting S to that one, and there are m connecting here, then obviously for each that I can choose here, I can choose another one here. So in short, what subproblem do I have to solve? I have to find non-intersecting path segments in this graph, and if I consider the conflict graph, if you want, of these path segments, then that's going to be a caudal graph. And I want to find weighted multicolored independent sets where the vertex weight is the number of paths, the weight of the independent set is the product of the vertex weights, and the colors correspond to the gaps that they close. And one other technical results that we showed is that this problem is also FPT with respect to the number of colors. And I think because of the time is running out, I'm going to skip over our approximation results, which I only wanted to mention anyway to conclude. So to the best of our knowledge, we initialized exploring the parameterized complexity landscape of temporal path counting. We showed that it's polynomial time solvable if the underlying graph is a forest, and then we showed a number of ways to generalize this. And in particular, we also showed that it's presumably not possible to generalize it to obtain FPT algorithms for the parameter feedback vertex number of the underlying graph or smaller parameters. And as future work in particular, we really wanted to know the parameterized complexity for the vertex cover number of the underlying graph, and we didn't really manage to do that. And I just wanted to mention that most of our results also seem to work if you want to count so-called restless temporal path that can only wait in a vertex for a certain amount of time, or if you want to count the delay robust routes that Malte talked about in the previous talk. Okay, here's a link to the archive manuscript, and thanks.
Thanks for the talk. Do we have any question on site or online? Yeah, there was a question from Andrea Marino. Maybe you can unmute and ask yourself.
Yeah, can you hear me?
Yes.
Yeah, okay. So thank you for the very nice talk. And just a remark. At some point, we were investigating also listing of enumeration of paths, of temporal paths, without repetition. And basically, there is a paper adapting, and counting somehow is related to listing, especially when it's hard to do. And there is a paper adapting basically the Johnson algorithm that is an algorithm for enumerating paths in simple graph with linear time delay. And so they adapted the Johnson algorithm to the temporal set. Now, since that algorithm is output sensitive, basically when you have a polynomial number of solutions, basically you get a polynomial algorithm also to count. Okay, so that's basically what I wanted to say. So for instance, I don't know, maybe this is the case of when the underlying graph is a forest.
I'm not sure, because let me try to draw this. So assume that your temporal graph,
I mean, it depends if it's undirected, if it is directed or undirected, because you can go.
I mean, if you have something like this, then you have 2 to the, let's say these are k vertices, then you have 2 to the k temporal path, right? So I think we thought about that a little bit, and I think in all of these cases that or almost all, I'm not completely sure, the cases that we considered, the number temporal path can be larger than our running time, meaning that our algorithms really are tailored to counting. They presumably cannot enumerate the temporal path. Also, if the underlying graph is a forest, I think that should be a little example, because here I can choose either of those two, and then either of those two, either of those two, either of those two, so I can get an exponential number of temporal path in total.
I see. Anyway, it could be interesting for maybe other.
Sure, yeah. I would be interested to have a look, so maybe you can send me.
I can send the link to the chat, for instance.
Okay.
Okay, thank you very much.
Okay, so now it's with the end of the session, so we can thanks Hendrik again and the rest of the speaker.
Thank you.